You lift your gaze and notice the moon resting gently above the horizon, its soft light reflecting off the quiet surfaces below. Its phases shift gradually, moving from a thin crescent to a full circle, revealing how its position relative to the sun and Earth changes steadily over time. The moon rises and sets with a predictable rhythm, and your mind traces these movements, feeling the subtle consistency in its orbit. You understand that the path of the moon is governed by gravity, the same force that pulls every object toward Earth, yet in balance with the moon's own momentum as it travels through space. Each night, as it appears slightly shifted from the previous evening, you sense the gentle tug of these invisible forces that have guided its motion for billions of years. You follow its influence down to Earth, where oceans respond in quiet obedience. The gravitational pull of the moon creates the tides, the rising and falling of vast waters in a measured cadence. High tides and low tides appear at regular intervals, a natural consequence of the moon's presence and position. You imagine the calculations early scientists performed, observing coastal waters, charting their heights, and linking these patterns to the distant glow above. The ocean's surface, though seemingly chaotic with waves and currents, carries the hidden rhythm of a precise celestial influence. You feel a sense of calm in recognizing this consistent pattern, a reliable pulse that echoes across both sky and sea. As your mind tracks the moon's path across the sky, you recall how ancient astronomers measured its size and distance. By observing lunar eclipses, noting the moon's shadow across Earth, they could estimate its diameter with careful geometry. You follow the steps, measuring angles, timing movements, and recording positions over months and years. These observations allowed humans to deduce that the moon is about 1/4 the diameter of Earth, and that it resides roughly 384,400 kilometers away. You picture the patience and care it required, standing outside in darkness with instruments designed to capture faint light, charting details that most passers-by would never notice. Each measurement is a quiet act of connection, a bridge between human curiosity and the vastness above. You consider the moon's surface itself, revealed to early telescopic observers as marked with craters, plains, and highlands. Scientists cataloged these features systematically, noting their size, shape, and distribution. You trace the contours in your mind, imagining the steady light of the sun illuminating jagged edges and smooth plains at different times. The craters, formed by impacts over billions of years, carry a record of the solar system's history. You sense the scale of time embedded in these features, each one a moment of energy and motion preserved on a celestial surface. Even without touching it, you understand the moon's landscape through careful observation and measurement. The moon does not move randomly. Its orbit follows a path known as an ellipse, a stretched circle with predictable dimensions. You watch as it travels around Earth, noticing that its distance fluctuates slightly, creating perigees and apogees, the closest and farthest points from our planet. These variations subtly affect tides, and even the apparent size of the moon as seen from Earth. You reflect on the mathematics underlying these motions, the work of astronomers like Kepler who identified the laws of planetary movement. Gravity, momentum, and distance intertwine, producing a system that is elegant in its reliability. Your mind rests in the knowledge that these forces are measurable, consistent, and understandable through careful study. You sense the moon's relationship with Earth in another way, through its effect on rotation. Tidal forces gradually transfer energy between Earth and the moon, slowing our planet's spin very slightly over millions of years. The length of a day has increased slowly, imperceptibly, as the moon drifts farther outward. You contemplate this gradual shift, observing the long-term impact of gravitational interaction. It is a reminder that even small forces, applied over vast spans of time, create measurable changes. Your thoughts follow the precise calculations of physicists and astronomers, who measure tiny deviations in motion to confirm these patterns. Each measurement reinforces your appreciation for the scale and precision of celestial mechanics. As you continue observing, you notice how the moon reflects sunlight rather than producing its own light. Its surface is covered in regolith, a layer of fine dust and rock fragments that scatters incoming light. You follow the reflection across its phases, seeing how the angle of sunlight creates shadows and craters and highlights the ridges of mountains. Scientists use this reflected light to study the moon's surface composition, mapping minerals and identifying regions with differences in density and texture. You imagine the slow accumulation of data over decades, building a detailed understanding of an object that floats silently above you. You think of the early space probes, which extended human observation beyond what telescopes alone could reveal. Spacecraft carried instruments to measure gravitational fields, surface temperatures, and chemical composition. You track how these readings confirmed calculations made centuries earlier from Earth-based observations. The moon is both familiar and measured, its properties documented with accuracy that continues to improve. You feel the patience and care inherent in these methods, the slow collection of facts that gradually fills in a complete picture of the lunar environment. Observing the moon also brings an awareness of its synchronous rotation. It keeps one face toward Earth constantly. You follow this pattern, understanding that tidal locking is a result of gravitational interaction over billions of years. You consider how this affects our perception of the moon, revealing only one hemisphere and leaving the far side hidden until spacecraft visited it. The phenomenon is predictable, yet it offers a sense of quiet wonder in the stability of natural systems. You reflect on how such details are confirmed through repeated measurement and consistent observation. As the night deepens, you notice the moon's color subtly shift from bright white to pale yellow near the horizon. Atmospheric scattering affects its appearance, yet its physical properties remain constant. Scientists account for these effects in their measurements, separating observation from interference. You sense the careful distinction between appearance and reality, the methodical approach that characterizes all scientific study. Your thoughts rest on the patient accumulation of knowledge, the evidence built from repeated and verified observation. You follow the moon's movement hour by hour, observing its slow arc across the sky. Its rising and setting are measurable, predictable, and gentle. You track its progress and the resulting changes in tides, shadows, and reflected light. Each night reinforces the reliability of gravitational forces, orbital mechanics, and observational science. The moon becomes a companion in your mind, a constant and quantifiable presence that grounds your thoughts in the precision of the natural world. You consider the historical efforts to communicate measurements across generations. Astronomers of the past relied on careful notes, sketches, and calculations, passing knowledge forward so that each new observer could refine and expand the understanding of the moon. You appreciate the continuity of scientific observation, the cumulative effort required to build a clear picture of an object so distant yet so influential. This awareness of time and method creates a slow, measured rhythm in your own thoughts, aligning your mind with the steady pace of celestial motion. Finally, you rest in the quiet knowledge that the moon's position, size, and motion are well understood. Every phase, every rise and fall of tides, every reflected beam of sunlight carries information confirmed through centuries of observation and measurement. Your mind settles into the rhythm of its orbit, the gentle consistency of forces and distances. In the stillness of night, you feel the careful order of the moon and Earth interacting, a reminder that even vast distances and immense scales obey rules that can be observed, measured, and understood. As your awareness lingers on this rhythmic motion, you begin to sense the subtle patterns that emerge in human curiosity and exploration, and how our understanding extends gradually from what is visible to the instruments that reach beyond, tracing the path of objects we have yet to visit directly. You turn your attention to the human fascination with the sky, noticing how our ancestors observed patterns in the moon, planets, and stars. They charted the night carefully, recording positions of celestial objects over years and decades. You follow the methods used to predict eclipses and the movement of planets, realizing that mathematical observation became the earliest form of space science. These early astronomers measured angles between stars and the moon using simple instruments like quadrants and astrolabes. They tracked the moon's phases with exacting consistency, noting the small variations in its motion caused by gravitational interactions with Earth and the Sun. You feel a quiet admiration for the patience and precision required in these observations, each entry in a log contributing to a cumulative understanding of the sky. You consider the work of thinkers who began to conceptualize motion beyond Earth's surface. By examining falling objects and the motion of planets, they understood that the same physical laws applied universally. You follow the path of Galileo, who observed lunar craters through his telescope and confirmed that the moon was a solid body with varying terrain, rather than a smooth, perfect sphere. You imagine looking through a telescope like his, slowly moving the lens to observe shadows in craters, seeing mountains and plains appear in detail. Each discovery expanded the known scale of the universe and set the stage for understanding how a human-made object could eventually leave Earth to reach these distant surfaces. You trace the early theories of rocketry, noting that engineers and scientists began to calculate the velocity needed to overcome Earth's gravitational pull. You learn that reaching orbit requires overcoming the downward force of gravity by accelerating to a speed that keeps an object in freefall around the planet. You follow the step-by-step reasoning behind these calculations, understanding that every rocket, whether experimental or theoretical, relies on precise measurements of mass, fuel, and thrust. You feel the steady logic of physics unfolding, a predictable system that can be harnessed to move objects from the surface into space. You think about the contributions of pioneers like Konstantin Tsiolkovsky, who formulated the rocket equation. He demonstrated that achieving high velocities required carefully managing fuel ratios and exhaust speed. You track the mathematics softly, appreciating the precision needed to reach even a fraction of Earth's escape velocity. Each variable, from the mass of the rocket to the force of the expelled gases, influences the trajectory, and small miscalculations could prevent ascent entirely. You sense the patient reasoning behind these principles, the slow accumulation of knowledge that eventually made spaceflight possible. You follow the work of Robert Goddard, who built the first liquid-fueled rockets. His experiments tested the principles of thrust, guidance, and stability. You notice how he measured flight paths, fuel consumption, and engine performance meticulously, using data to refine designs. The small rockets of early experiments were not yet capable of reaching orbit, but they provided a solid foundation for understanding propulsion. You feel the care and methodical repetition in these trials, the attention to every detail, from nozzle design to fuel mixture, that allowed progress to accumulate steadily over years. You observe how multiple nations began developing space science independently, often drawing from military and atmospheric research. You follow the launch of sounding rockets, which carried instruments to measure temperature, pressure, and radiation at high altitudes. These measurements created the first empirical understanding of conditions beyond the surface. You consider the meticulous collection of data, the careful calibration of instruments, and the verification of results through repeated flights. This methodical approach allowed humans to expand their reach incrementally, moving closer to the vacuum of space with every ascent. You notice the challenges of traveling beyond Earth. The vacuum of space presents a complete lack of air for propulsion, requiring rockets to carry oxidizer along with fuel. Temperatures vary drastically, and radiation from the sun and cosmic sources poses constant risk. You track how early scientists predicted these conditions using calculations and observations, estimating pressures, temperatures, and particle densities at various altitudes. Your mind absorbs the scientific approach. Quantify, measure, predict, and verify. Each calculated risk became a step towards safely sending objects, and eventually humans, beyond Earth's protective atmosphere. You reflect on the first attempts to reach orbit, noting the incremental increases in altitude and velocity. Each test flight provided precise data about acceleration, trajectory, and stability. Failures were as informative as successes, revealing physical limits and areas for improvement. You imagine engineers poring over flight logs, analyzing the performance of engines, guidance systems, and structural materials. Slowly, patterns emerged that allowed rockets to achieve higher velocities, longer flights, and more predictable paths. You sense the steady progression of knowledge, each experiment building upon the last. You consider the mathematics of orbital mechanics. To reach the moon, a spacecraft must first enter orbit around Earth, then transfer to a trajectory intersecting the moon's path. You follow the calculations of delta V, launch windows, and orbital alignments. Every maneuver depends on precise timing, because even small deviations can result in a missed target. You feel the calm exactness of these calculations, the predictable interplay of mass, velocity, and gravitational forces that govern movement in space. By observing these principles, you see how human curiosity and scientific reasoning combine to extend exploration beyond familiar horizons. You notice how cultural interest in the moon influenced scientific effort. Stories and observations inspired generations to seek empirical answers rather than rely solely on imagination. Astronomers cataloged features systematically, while engineers designed vehicles capable of escape velocity. You follow the chain of knowledge, from sketches in notebooks to physical experiments, recognizing the slow, cumulative growth of understanding. Each recorded measurement, each carefully logged experiment, gradually transformed curiosity into capability. You sense the rhythm of discovery, a steady pulse of careful observation and verification that persists across decades. You feel the gradual convergence of theory and practice. Observations of lunar motion, the laws of planetary mechanics, and experiments in rocketry all combine into a coherent understanding of how human-made objects could leave Earth. You trace the historical sequence of ideas, calculations, and trials, seeing how each contribution informed the next. There is a quiet satisfaction in observing the logical consistency of physical laws, and how human ingenuity aligns with those laws to achieve controlled movement in space. As the night deepens, you rest in the awareness that these early experiments and observations laid the groundwork for actual spaceflight. Every calculation, flight test, and measurement contributed to a slow, methodical approach that eventually made a journey to the moon possible. Your mind absorbs the careful balance of forces, the energy calculations, and the precise timing that governs all motion beyond Earth. You feel a gentle connection to the early explorers of the sky, understanding that patient reasoning and meticulous experimentation prepared the way for humans to leave the ground and travel among the stars. In this quiet reflection, you begin to sense how the transition from mathematical prediction to human spaceflight relied on both precise engineering and a deep understanding of natural laws, forming a bridge between imagination and the reality of leaving Earth behind. You imagine the early 1960s, when human spaceflight had begun but the moon remained distant and unvisited. Engineers and scientists across the United States studied how to move beyond low Earth orbit, combining knowledge of physics, materials science, and mechanics. You follow their work as they calculate the enormous velocities required to reach the moon, recognizing that overcoming Earth's gravity demands precise control of acceleration and fuel consumption. Every calculation is verified through repeated simulations and tests, building a solid foundation for practical mission planning. You notice the creation of the Saturn V rocket, a structure of immense scale designed to carry both astronauts and equipment beyond Earth's protective atmosphere. Each stage of the rocket serves a precise purpose. The lower stages provide the initial thrust to escape gravity, while the upper stages place the spacecraft into orbit and on a trajectory toward the moon. You track the logic behind staging, seeing how shedding mass at specific points allows the vehicle to accelerate more efficiently. You feel the careful reasoning that translates fundamental physics into functioning machinery capable of reaching a distant world. You follow the spacecraft itself, designed to sustain life in the vacuum of space. The command module houses astronauts during transit, providing oxygen, temperature control, and protection from radiation. The lunar module is a smaller, specialized craft, capable of descending to the moon's surface and returning to orbit. You observe the engineering required to maintain air pressure, filter carbon dioxide, and manage temperature, all while keeping mass as low as possible. Each detail reflects a deep understanding of human physiology in microgravity and the exacting requirements of spaceflight. You notice the extensive training astronauts undergo to prepare for microgravity and lunar conditions. They practice navigation, docking, and extravehicular activity, learning to move in an environment where every motion follows Newton's laws precisely. You watch simulations of lunar landings, where engineers use detailed maps and models to recreate surface slopes, craters, and boulders. By studying these scenarios, astronauts learn to make decisions with predictable results, relying on carefully calculated guidance systems and the physics of motion in low gravity. You consider the orbital mechanics involved in a moon mission. Once in Earth orbit, a spacecraft must perform a translunar injection to place it on a trajectory intersecting the moon's orbit. You follow the timing, angles, and velocity changes required to ensure the spacecraft arrives at the correct point in space. Even small errors can cause a miss, so calculations are refined repeatedly, verified with simulations and tracked using telemetry. You feel the precision of the process, each adjustment grounded in exact principles of motion and gravity. You reflect on the navigation systems developed to maintain orientation and trajectory. Gyroscopes, star trackers, and onboard computers allow spacecraft to monitor position and velocity accurately. You observe how engineers integrate measurements of the moon's position, spacecraft acceleration, and fuel consumption to make fine corrections in flight. Every input is measured, every output verified, forming a continuous loop of feedback that guides the spacecraft safely toward its target. The reliability of these systems rests on both careful design and repeated testing. You trace the early missions that preceded a moon landing, such as Mercury and Gemini, which tested critical technologies and human endurance. These missions demonstrated spacecraft control, orbital rendezvous, and long-duration habitation in microgravity. You sense how each accomplishment gradually increased confidence in the feasibility of traveling farther. The methods used to measure success are precise and scientific. Velocity tracking, environmental monitoring, and physiological assessment all contribute to understanding the effects of spaceflight on humans. You observe the testing of materials and structures for re-entry and landing. Heat shields are engineered to withstand thousands of degrees Celsius during descent through the atmosphere, while hulls must resist both pressure and micrometeoroid impacts. You follow the reasoning behind selecting alloys and composites, balancing strength, weight, and thermal properties. Engineers test components repeatedly under controlled conditions, gathering data to confirm predictions of performance. Each trial reflects an incremental step toward a reliable system capable of protecting astronauts during critical phases of the mission. You consider the human factors carefully studied by engineers and scientists. Life support systems are designed to maintain temperature, humidity, and air composition. Food, water, and waste systems are calibrated for both efficiency and safety. You notice the integration of redundancy, ensuring that critical systems have backups in case of failure. These considerations are based on empirical evidence and understanding of human biology, reinforcing that exploration beyond Earth demands meticulous attention to survival in an environment that is fundamentally hostile to life. You watch as mission planners calculate launch windows with extreme precision. The moon's position, Earth's rotation, and orbital mechanics all determine the timing required for a successful flight. You follow the logic of aligning trajectories so that the spacecraft arrives at lunar orbit with minimal fuel expenditure and maximum accuracy. Every decision is backed by data, calculations, and simulations, forming a methodical chain that gradually brings the goal within reach. You think about communication systems that connect astronauts to Earth. Radio waves travel across hundreds of thousands of kilometers, allowing continuous monitoring of vital signs, position, and spacecraft status. You trace how signals are transmitted, received, and interpreted, noting the careful synchronization required to avoid errors. This constant exchange of information ensures that every movement can be tracked and corrected, a living example of how observation and measurement are fundamental to spaceflight. You follow the planning of the lunar landing itself, where the final descent is controlled with fine thruster adjustments. The lunar module must navigate shadows, slopes, and craters, guided by both instruments and astronaut observation. You notice the calculation of fuel margins, speed limits, and angles of descent, all derived from physics and past data. Each factor is measured and monitored, leaving nothing to chance. You sense the quiet assurance provided by understanding forces, velocities, and trajectories rather than relying on intuition alone. You observe how engineers account for contingencies, including system failures and unexpected conditions on the lunar surface. Backup procedures are mapped, with every potential outcome considered and tested. You trace how redundancies in navigation, life support, and power allow the mission to continue safely even if individual components fail. The careful planning demonstrates the application of logic, measurement, and evidence to ensure human survival in a remote environment. You feel the slow unfolding of a complex network of science and engineering, each step building upon the last. Every calculation, test, and simulation brings the possibility of reaching the moon closer to reality. You sense the alignment of human curiosity with the predictable laws of physics, producing a deliberate and methodical approach to exploration. Each element, from fuel calculations to life support, integrates into a coherent system designed to operate reliably under extreme conditions. As your awareness settles on these preparations, you notice how the combination of physics, engineering, and human determination begins to form a bridge between Earth and the moon. Every measurement, simulation, and calculation brings the distant surface into reach, creating a framework that allows humans to travel beyond their home planet with confidence and precision. You watch as the Saturn V rocket lifts off, its engines producing immense thrust to overcome Earth's gravity. You feel the gradual acceleration as the spacecraft climbs through the atmosphere, noting how every stage is designed to shed weight and improve efficiency. The lower stages burn fuel rapidly, pushing the craft skyward, while the upper stages are lighter and focused on achieving the speed needed to enter orbit. You follow the trajectory closely, understanding that reaching the moon requires precise calculations of velocity, angle, and timing. You notice the transition from atmospheric flight to microgravity. As the rocket passes beyond the densest layers of air, the vehicle experiences reduced resistance, allowing it to accelerate more efficiently. You trace the physics of freefall, recognizing that once the spacecraft reaches orbital speed, it is essentially falling around Earth rather than toward it. This balance of momentum and gravitational pull creates a stable orbit, where astronauts can experience weightlessness. You sense the subtle shifts in forces and the careful design that makes these conditions predictable and manageable. You consider the translunar injection, the maneuver that propels the spacecraft out of Earth orbit toward the moon. You follow the timing of engine burns, the calculation of trajectory, and the precise alignment required to intersect the moon's path. Every second of the burn affects arrival position, velocity, and angle of approach. You observe how engineers simulate these events repeatedly, refining parameters and accounting for minor variations in mass, fuel load, and gravitational effects. The process reflects the careful application of orbital mechanics, allowing the spacecraft to travel hundreds of thousands of kilometers with remarkable precision. You think about navigation during the journey. Astronauts rely on both onboard instruments and observations of celestial objects. Gyroscopes track orientation, while star sightings and calculations confirm position. You notice how small adjustments in trajectory are made using reaction control thrusters, ensuring the spacecraft remains on the intended path. Each correction is based on careful measurement and understanding of forces, demonstrating the reliability of physics even across vast distances. You feel the consistency of these systems, and the quiet assurance that motion in space follows predictable patterns. You follow the approach to the moon, where its gravity begins to subtly influence the spacecraft's path. You notice how flight controllers calculate lunar orbit insertion, adjusting velocity so the craft can be captured into a stable orbit around the moon. This requires understanding the balance between the moon's gravitational pull and the spacecraft's momentum. You sense the gentle precision involved, where small changes can significantly affect the orbit, and recognize the importance of repeated calculations, simulations, and constant monitoring during this phase of flight. You observe the planning of the lunar module's descent. The module separates from the command module and begins a controlled approach to the surface. You track the physics of deceleration, thrust, and gravitational influence as the vehicle slows to a safe landing speed. Pilots adjust for slopes, craters, and small obstacles, relying on a combination of instruments and visual cues. You notice how fuel margins, engine performance, and the module's mass are all carefully considered, allowing the descent to proceed safely and precisely. You reflect on the moon's gravity, which is roughly 1/6 of Earth's. This affects every maneuver, from landing to movement on the surface. You imagine how astronauts must adapt their walking, using slower, deliberate motions, and how instruments designed for Earth conditions respond differently. The reduced gravity also affects trajectory calculations, requiring adjustments for ascent, rendezvous, and return to orbit. You sense the necessity of understanding these forces fully before any mission is attempted, highlighting the careful interplay between prediction and observation in space travel. You follow the astronauts' experience in microgravity. They move slowly and deliberately, conserving energy and maintaining control. You notice how life support systems continuously regulate air composition, temperature, and pressure, ensuring a stable environment. You consider the precision required in maintaining these systems, the careful monitoring of oxygen, carbon dioxide, and humidity. Every reading confirms that the spacecraft provides a safe habitat, and the crew's experience remains predictable, demonstrating the reliability of engineering and scientific planning. You observe the role of communication during the journey. Radio signals are transmitted over hundreds of thousands of kilometers, allowing Earth-based mission control to monitor position, velocity, and environmental conditions. You follow the process of sending commands and receiving telemetry, noting the exact timing required to account for signal travel delays. Each message confirms calculations, guides maneuvers, and reassures the crew that their position and systems are stable. The process exemplifies how human observation extends across space, connecting distant locations through physics and technology. You consider the orbital mechanics of rendezvous between the lunar module and command module. Timing is critical. Each spacecraft must meet at a precise point in orbit to allow docking. You trace the calculations that predict paths, velocities, and angles of approach. Small thruster burns adjust positions, following principles of momentum and gravitational influence. The synchronization of these movements is based entirely on physics and repeated simulation, showing how careful planning allows objects to meet in the vast emptiness of space with predictable outcomes. You notice the precautions taken against hazards such as radiation and micrometeoroids. Spacecraft shields, mission duration limits, and trajectory planning reduce exposure. Instruments measure radiation levels, and designs include redundancies to ensure safety. You observe the data collected, the calculations performed, and the constant monitoring that make travel through space manageable despite inherent risks. Each protective measure is grounded in observation, experimentation, and the known properties of space. You reflect on the gradual approach to the moon's surface. The lunar horizon grows more defined as the module descends. You follow the careful observation of terrain, the evaluation of slopes, and the identification of landing zones. Pilots adjust in response to these measurements, relying on instruments and precise calculation. Every action corresponds to a known physical principle, from gravitational acceleration to momentum conservation. You sense the predictability of motion and the effectiveness of prior planning in making a controlled landing possible. You observe the spacecraft in stable lunar orbit, a silent presence circling the moon as astronauts prepare for descent. You notice the interplay between velocity, gravity, and trajectory that keeps it moving in a continuous path. The calculations that maintain orbit are exact and repeatable, confirming the reliability of Newtonian mechanics over large scales. You feel a sense of calm in the orderliness of these movements, appreciating how predictable patterns allow humans to operate safely in environments far from Earth. You rest in the awareness that reaching the moon is the result of a precise balance between forces, timing, and careful observation. Every maneuver, burn, and adjustment is based on measurable physical laws, from propulsion to orbital mechanics. The journey is deliberate, controlled, and verified at every step. As your mind follows the spacecraft's path, you begin to sense the next challenge. Understanding the moon itself, its surface, composition, and the careful measurements required to explore it directly. You watch as the lunar module descends gently toward the moon's surface, its thrusters counteracting gravity with careful precision. The lander touches down on the gray, dusty terrain, and you notice the subtle displacement of fine regolith under its weight. Every movement is deliberate, and the astronauts' observations begin immediately. You follow their careful documentation of surface features: rocks, craters, and gentle slopes. Measurements of angles, distances, and textures are recorded systematically, forming the basis for scientific understanding of a world previously observed only from afar. You consider the composition of lunar rocks, which astronauts categorize into different types based on density, mineral content, and formation processes. Basaltic rocks indicate past volcanic activity, while lighter anorthosite suggests ancient highlands. You notice how each sample is carefully handled, logged, and packaged for return to Earth. Laboratory analysis confirms the chemical composition, revealing the presence of elements such as silicon, oxygen, magnesium, and iron. These observations are consistent with prior remote sensing data, reinforcing confidence in predictive models of the moon's formation and structure. You trace the methods used to measure soil properties. Regolith samples are analyzed for particle size, porosity, and cohesion. You observe how scientists determine the bearing strength of the soil, informing predictions about surface stability and the behavior of vehicles and habitats. Small, controlled experiments such as foot impressions and will tracks provide additional insight into the interaction between lunar soil and human or robotic equipment. Every observation is linked to a broader understanding of material science and planetary geology. You notice the deployment of instruments designed to monitor environmental conditions. Seismometers detect vibrations caused by meteorite impacts, internal shifts, and even distant earthquakes on Earth. You follow the data as it arrives, showing small, regular signals and occasional larger impulses. This information allows scientists to map the internal structure of the moon, identifying layers of crust and mantle, and estimating the density of materials beneath the surface. You sense the slow accumulation of precise data, each measurement contributing to a comprehensive picture of lunar geology. You reflect on the use of retroreflectors, small mirrors placed on the lunar surface to reflect laser beams sent from Earth. You imagine scientists on Earth aiming lasers at these devices, timing the travel of light with extraordinary precision. The measurements reveal the exact distance between Earth and the Moon, accurate to a few centimeters. You feel the meticulous nature of these observations, the combination of technology and patience allowing humans to measure interplanetary distances directly. These measurements confirm predictions made centuries earlier by astronomers observing the Moon from Earth. You consider how temperature variations on the Moon are recorded and studied. Without an atmosphere, the surface experiences extreme changes, from intense heat in sunlight to deep cold in shadow. Thermometers and thermal sensors capture these fluctuations, providing insight into material properties, heat transfer, and environmental conditions that spacecraft and future habitats must endure. Each reading is verified against calculations, confirming the predictable response of lunar material to solar radiation. You sense the clarity and reliability of science, grounded in measurement rather than speculation. You follow the careful cataloging of surface features. Craters are measured, mapped, and compared to images taken from orbit. Scientists use these measurements to determine the frequency and size of meteorite impacts over billions of years. You notice how the distribution of craters informs estimates of surface age and geological history. Every detail, from crater diameter to depth, is recorded precisely, forming a database that continues to guide understanding of the Moon's evolution. You observe the use of core samples to probe beneath the lunar surface. Cylindrical sections of soil reveal layers that accumulated over time, preserving a record of environmental changes, volcanic activity, and impact events. You track how each layer is measured and analyzed, noting variations in composition and density. These samples provide a timeline of the Moon's history, allowing scientists to reconstruct events long before humans existed. You feel the quiet satisfaction of data building a narrative grounded entirely in evidence. You notice the collection of data on solar wind and cosmic rays. Instruments measure the flux of charged particles striking the Moon, revealing patterns in solar activity and radiation exposure. You consider the implications for both human safety and planetary science, understanding how these measurements inform protective designs for future explorers. Each recorded particle, each measured fluctuation, contributes to a detailed map of the Moon's interaction with the Sun and the space environment. You sense the careful diligence in observation, translating small signals into broader knowledge. You reflect on the visual documentation of the surface. Photographs and videos capture shadows, textures, and the interplay of light and topography. These images are not only records of human presence but scientific tools for analysis. You observe how different angles of illumination reveal subtle variations in surface features, aiding in geological interpretation. Every image is accompanied by measurements, coordinates, and observational notes, creating a comprehensive scientific record. You appreciate the systematic approach, where observation, measurement, and documentation are inseparable. You consider how experiments on the moon provide insight into mechanical properties. Tools such as penetrometers and simple dropping devices allow measurements of surface hardness and elasticity. These experiments confirm theories developed from remote sensing and physical modeling. You follow the methodical application of these tests, observing how repeated trials ensure accurate results. Each experiment is designed with precision, reflecting the careful planning required to conduct science in an environment that cannot be modified freely or easily corrected. You notice the integration of multiple data streams. Seismometers, reflectors, photographs, and samples all combine to form a detailed understanding of the lunar environment. Data from one instrument informs interpretation of another, creating a coherent picture of geology, composition, and physical properties. You sense the satisfaction of seeing disparate observations converge, forming a model that accurately represents an unfamiliar world. The moon becomes less abstract and more fully measurable, its properties defined through empirical evidence. You reflect on the precision of these scientific efforts. Every observation is documented, every experiment carefully planned, and every sample preserved. You sense the continuity between Earth-based predictions and the measurements taken directly on the lunar surface. Human curiosity, guided by careful methodology, allows you to follow and understand processes that operate across vast distances and timescales. You feel the steady accumulation of knowledge, each data point a building block in the structure of planetary science. As your mind rests on these observations, you begin to sense the broader implications of lunar exploration. The moon provides a laboratory for understanding planetary processes, a testing ground for instruments and methods, and a source of precise measurements that refine models of celestial mechanics. Its surface, silent and unchanging over centuries, offers reliable data that continues to inform our understanding of Earth, space, and the forces that govern motion across the solar system. You begin by noticing the global environment in which lunar exploration took place. The mid-20th century was marked by intense competition between nations, particularly the United States and the Soviet Union. You follow how political objectives influence scientific planning, with governments allocating funding, personnel, and resources to advance spaceflight. Every decision, from rocket development to mission scheduling, was informed by careful evaluation of both technical feasibility and national priorities. You sense the interplay between strategy and engineering, where scientific goals were pursued within the context of larger societal pressures. You observe the establishment of NASA as a centralized organization tasked with achieving human spaceflight objectives. Its creation allowed for coordinated research, testing, and mission management. You notice how scientists, engineers, and administrators work together to balance technical requirements with political timelines. Every project involved multiple teams, each responsible for specific tasks such as propulsion, navigation, communications, and life support. You feel the structured methodology applied to complex problems, demonstrating how organized planning enables ambitious objectives to be achieved. You consider the funding and resource allocation required for the Apollo program. Billions of dollars were directed toward research, development, and testing, supporting thousands of scientists, engineers, and technicians. You follow the procurement of materials, construction of testing facilities, and design of launch complexes. Every aspect was documented, analyzed, and scheduled meticulously. You sense the reliance on empirical evaluation, whether testing engines, validating guidance systems, or modeling orbital trajectories, ensuring that public investment produced reliable results. You reflect on international awareness of the space race. Other nations observed launches, trajectories, and achievements through telescopes, radar, and tracking stations. Scientific publications and data sharing allowed independent verification of events such as orbital insertions and lunar landings. You notice the role of open observational evidence in confirming accomplishments, illustrating that even politically motivated efforts depended on verifiable measurements to maintain credibility. You feel the quiet authority of empirical observation amid geopolitical tension. You follow the influence of national ambition on technical decisions. Timelines, mission priorities, and target objectives were informed by both scientific and symbolic considerations. Launch dates, crew selection, and mission milestones were scheduled with precision, integrating physics, engineering constraints, and political pressures. You sense how careful modeling, simulations, and testing ensured that the spacecraft could perform reliably even under strict deadlines, illustrating the interplay between human ambition and natural laws. You consider the societal impact of lunar exploration. Public interest and media coverage created pressure to demonstrate tangible progress. Educational outreach and scientific reporting helped communicate the methods, findings, and measurements underlying each mission. You observe how engineers and scientists described results in precise, measurable terms, whether detailing orbital insertion angles, fuel margins, or sample compositions. The clear distinction between observation and interpretation allowed audiences to understand achievements without exaggeration or embellishment. You notice how technological development accelerated in response to political goals. New materials, propulsion systems, and computing devices were created to meet mission requirements. Each advancement was tested, measured, and refined. You trace the evolution of guidance computers, which calculated trajectories in real time, monitoring velocity, acceleration, and orbital parameters. You feel the consistent reliance on empirical validation, confirming that every new technology integrated into the program performed predictably and safely. You observe the broader scientific opportunities created by the program. Beyond achieving a lunar landing, the missions provided long-term data on orbital mechanics, microgravity, radiation exposure, and human physiology. You follow the systematic recording of environmental parameters, experiment results, and surface observations. Each measurement was carefully logged and analyzed, providing knowledge that extended well beyond the political objectives that initially motivated the missions. You sense the subtle way scientific discovery progresses even amid external pressures. You consider the role of rigorous training and simulation in preparing astronauts. Mission rehearsal, equipment testing, and emergency procedure practice were conducted repeatedly. You notice how these exercises allowed the crew to respond accurately to unexpected variables, relying on precise data rather than intuition alone. Every simulation reinforced measurements of acceleration, orbital adjustments, and environmental conditions. You feel the calm confidence that arises from preparation grounded in observation and repeatable methods. You follow the careful documentation of all aspects of the program. Reports, logs, and recordings capture data on engine performance, navigation, communication, and life support. You notice how each detail is verified against measurements and simulations, providing a comprehensive record of progress. Even as political and cultural forces shaped priorities, empirical evidence remained central to decision-making. You sense that structured, evidence-based approaches create stability and reliability in complex human endeavors. You reflect on the interaction between public perception and scientific measurement. Announcements of launches, orbit insertions, and lunar landings were accompanied by verifiable evidence, telemetry data, photographs, and independent observations. The reliance on measurable outcomes allowed both scientists and the public to evaluate claims objectively. You appreciate the way empirical validation bridges the gap between ambition and reality, grounding human aspiration in observable fact. You notice the integration of multiple disciplines in achieving program goals. Physics, engineering, geology, biology, and computing all contributed to the success of lunar exploration. Each field relied on observation, measurement, and controlled experimentation. You follow the systematic coordination of these disciplines, seeing how precise data collection informs engineering decisions, mission planning, and safety protocols. You feel the quiet order that emerges when diverse scientific approaches converge toward a common, measurable objective. You consider how the Apollo program serves as an example of structured problem-solving under complex constraints. Every challenge, whether technical, logistical, or political, is addressed through analysis, testing, and verification. You observe how calculations of orbital trajectories, fuel requirements, and surface conditions are rigorously checked against experimental data. The result is a methodical system in which human curiosity, political will, and physical laws align to produce verifiable outcomes. As your awareness rests on these observations, you notice how political and cultural forces, when paired with careful measurement and methodical planning, can accelerate scientific progress. The structured approach ensures that exploration is both ambitious and reliable, and it begins to hint at the next phase, the detailed study and sampling of the moon itself, where measurement and observation translate directly into new knowledge about another world. You begin by observing the immense scale of investment required to send humans beyond Earth. The Saturn V rocket, launch facilities, spacecraft, and mission control centers were all products of years of planning, engineering, and funding. Each component involved thousands of engineers, technicians, and scientists, working in unison to ensure reliability and safety. You follow the budgeting process, noting how every dollar spent was justified by technical necessity, safety requirements, and anticipated scientific return. Understanding these calculations allows you to see exploration not as a single event but as the cumulative result of deliberate financial planning. You notice how research and development accounted for a significant portion of total costs. Propulsion systems, navigation computers, life support modules, and communication infrastructure each demanded careful testing and refinement. Every test, from static engine firing to orbital simulations, represents hours of labor, material usage, and financial investment. You sense the detailed planning required to ensure that resources are used efficiently, reducing waste while increasing the likelihood of mission success. Each dollar allocated corresponds directly to an increase in precision and safety. You consider the costs associated with astronaut training. Each crew member spent months preparing for microgravity, lunar surface operations, and emergency scenarios. Simulations of lunar landings, navigation, and extravehicular activity required specialized equipment and facilities. You observe how training schedules are structured to maximize skill acquisition, relying on data from prior missions and experiments to create realistic practice scenarios. The investment in human preparation reflects the understanding that even small errors could have significant consequences, and that careful rehearsal is both scientifically and economically essential. You trace the operational expenses of maintaining mission control and ground tracking. Telemetry systems, communication satellites, and radar installations were maintained continuously, providing constant monitoring of spacecraft. You follow how engineers coordinate real-time data on trajectory, fuel consumption, and astronaut health. Each system requires infrastructure, staffing, and redundancy, all contributing to overall cost. You feel the precision inherent in these operations, ensuring that every signal received informs accurate decision-making and risk management. You notice the logistics of spacecraft production. Materials had to meet exact specifications for strength, thermal resistance, and radiation protection. Fabrication processes involved multiple stages of inspection and testing, verifying that every component met strict tolerances. You follow the cost calculations for manufacturing, understanding that higher quality materials and meticulous assembly reduce the probability of failure. Each investment in reliability ensures that scientific data is collected safely and consistently. You reflect on mission planning as an economic calculation. Each launch window, trajectory, and landing site is carefully chosen to minimize fuel use and maximize safety. Scientists and engineers model different scenarios, weighing risk versus benefit and resource expenditure. You sense the gentle logic in this approach. Cost is not simply money, but the allocation of limited energy, time, and materials to achieve reliable results. Every decision demonstrates a methodical balance between ambition and practicality. You consider the cost of risk management. Redundant systems, backup procedures, and contingency planning are all designed to prevent catastrophic failure. You observe how additional layers of safety require both financial and technical investment. Life support, propulsion, and navigation each have backups that increase mass, complexity, and expense. Yet each added system improves the likelihood of mission success and the integrity of scientific data. You feel the calm reassurance provided by thorough planning and measurement. You follow the calculations behind the frequency of lunar missions. Early Apollo flights were spaced to allow for careful evaluation of prior missions, recovery of lessons learned, and maintenance of equipment. The interval between launches reflects both technical and economic constraints, illustrating that exploration requires patience as well as resources. You notice how engineers and planners use empirical data to adjust schedules, ensuring that each mission is both feasible and cost-effective. The pacing reinforces the measured, deliberate approach necessary for success. You observe the financial implications of scientific instrumentation. Experiments, cameras, seismometers, and sample containers had to be designed to survive launch, microgravity, and the lunar environment. Each instrument was evaluated for cost, weight, and reliability. You follow the planning process that prioritized instruments offering the highest scientific return relative to expense. Every piece of equipment is chosen with data and measurement in mind, demonstrating that scientific discovery is tightly interwoven with careful resource allocation. You notice the integration of multiple cost factors into a comprehensive budget. Launch vehicles, spacecraft, astronaut support, ground operations, and instrumentation all combine into a detailed financial plan. You follow the process of reviewing each component, verifying projected outcomes against empirical data and previous experience. Every expense is justified with evidence of necessity, whether it is a new rocket stage, a safety feature, or a specialized training module. You feel the calm precision of planning that ensures investments yield measurable results. You consider how these financial and resource constraints shaped long-term exploration. Budgets limit the number of missions, the duration of stays, and the complexity of experiments. You trace the careful calculations used to determine which scientific objectives are achievable within cost and safety limits. Every mission represents a compromise between ambition and practical feasibility, grounded in measurement and evidence. You appreciate that rational limitations guide exploration, ensuring that every effort is both productive and sustainable. You reflect on the scale of human endeavor involved. Thousands of individuals, billions of dollars, and decades of preparation all converge to enable exploration of another world. You sense the discipline required to harmonize financial constraints, engineering limitations, and scientific ambition. Each decision is backed by calculation, testing, and verification, demonstrating that successful space exploration is as much an exercise in careful resource management as it is in physics or engineering. You rest in the awareness that economic considerations are inseparable from technical feasibility. Careful measurement, evaluation, and planning ensure that human exploration is deliberate, precise, and sustainable. Every calculation of cost corresponds to a calculation of risk, safety, and potential scientific gain. Your mind absorbs the understanding that exploring the moon involves balancing resources, knowledge, and ambition with the immutable laws of physics. As you reflect, you begin to sense the next dimension of preparation. Understanding the physical challenges of space itself, where the environment tests the limits of both human physiology and engineered systems, requiring continuous observation, calculation, and mitigation. You begin by noticing the environment beyond Earth's atmosphere, a realm devoid of air, with extreme temperatures and constant exposure to cosmic radiation. Every step of human spaceflight must contend with these conditions, each of which challenges both physiology and technology. You follow the calculations of radiation exposure, tracing how energetic particles from the sun and cosmic rays penetrate spacecraft walls. Shielding is designed to reduce dosage to safe levels, using materials chosen for their density, atomic number, and weight efficiency. You sense the balance between protection and practicality, where too much mass reduces fuel efficiency while too little endangers astronauts. You observe the effects of microgravity on the human body. In the absence of Earth's constant pull, muscles and bones experience reduced load. Astronauts perform daily exercises to maintain strength and prevent bone density loss. You follow measurements of cardiovascular function, noting changes in heart rate, blood volume, and fluid distribution. Every physiological response is monitored carefully, feeding data into predictive models that guide mission duration and activity scheduling. You feel the deliberate approach to maintaining health, where observation and measurement guide each preventive step. You consider the challenges of life support in a vacuum. Oxygen must be supplied continuously, while carbon dioxide is removed with high efficiency. Temperature and humidity are regulated to maintain comfort and safety. You observe the monitoring of atmospheric pressure, detecting minor variations that could affect both human physiology and equipment performance. Redundant systems ensure that a failure in one module does not compromise the crew. Each function is based on empirical understanding of physical and chemical processes, demonstrating the precise application of science to survival. You follow the management of fluids and waste. Water is stored, filtered, and recycled to support life in confined conditions. Waste collection and containment systems are engineered to prevent contamination, with careful attention to mass, space, and functionality. Every component undergoes testing to verify performance in microgravity, where liquids behave differently than on Earth. You notice how observation of fluid dynamics and material properties informs design decisions, reducing risk and ensuring reliability. You observe the planning required to prevent collisions with micrometeoroids and orbital debris. Spacecraft surfaces are reinforced in vulnerable areas, with multiple layers of material absorbing and dispersing impact energy. You follow how orbital calculations predict regions of higher debris density, guiding trajectory adjustments. Each precaution is quantified, allowing engineers to balance safety with fuel and mass constraints. You feel the precision in anticipation and response, demonstrating that motion and impact in space follow predictable laws when properly calculated. You notice the effects of prolonged isolation on psychological health. Confined quarters, limited sensory stimuli, and extended periods away from Earth can stress cognitive and emotional systems. Mission planners implement routines, schedules, and communication strategies to maintain mental well-being. You follow the systematic monitoring of sleep, stress, and alertness, with adjustments informed by observation rather than guesswork. Every procedure is designed to maintain functionality and ensure that the crew can respond accurately to challenges. You consider the dangers of launch and re-entry. Accelerations reach several times Earth's gravity, producing forces that affect cardiovascular and musculoskeletal systems. You follow the calculations of thrust, trajectory, and aerodynamics, ensuring that spacecraft structures withstand the stresses of ascent and descent. Heat shields are engineered to absorb and radiate thousands of degrees of thermal energy during atmospheric re-entry. You notice how materials are selected and tested to meet exact specifications, with measurements confirming that performance matches predictions. You trace the influence of vacuum on equipment. Lubricants, electrical systems, and mechanical components behave differently without air. Engineers test devices under controlled vacuum conditions, measuring wear, conductivity, and thermal properties. Every design decision relies on observed behavior rather than assumption, reducing the likelihood of malfunction. You sense the reliability that comes from observing phenomena and applying empirical data, creating systems that function predictably in an environment that would otherwise disrupt standard engineering solutions. You follow the management of energy resources. Power must be generated, stored, and distributed efficiently. Solar arrays, batteries, and fuel cells provide energy, each monitored for output and degradation. You notice how engineers plan contingencies, calculating the effects of unexpected shading, equipment failure, or prolonged operation. Redundant systems allow continued functionality, with measurements of performance informing adjustments in real time. You feel the calm certainty provided by detailed monitoring and predictive modeling. You observe the mitigation of radiation effects on electronics and crew. Electronics are shielded, error-correcting codes are used, and critical systems are duplicated. Astronauts wear dosimeters that measure accumulated radiation, and mission planners calculate exposure limits based on both current readings and projected solar activity. You follow the process of scheduling activities to minimize risk, including timing spacewalks and planning trajectories to avoid periods of heightened solar flux. Each action is guided by precise measurement, prediction, and established physical principles. You notice the planning required for contingency scenarios. Systems are designed with multiple levels of redundancy, and crew training includes procedures for equipment failure, medical emergencies, and navigational anomalies. You follow how each possible outcome is analyzed, simulations are run, and response strategies are prepared. The reliance on controlled observation and calculation ensures that unexpected events can be managed with predictable effectiveness. You feel the reassurance of preparation grounded in empirical knowledge. You reflect on communication reliability. Data transmission must account for distance, signal delay, and interference. Engineers monitor signal strength, antenna orientation, and frequency allocation. You notice how redundancy in communication pathways allows mission control to maintain oversight, while onboard instruments continuously verify data integrity. Every measurement ensures that information flows accurately between Earth and the spacecraft, reducing uncertainty and supporting safe operations. You follow the management of fuel and propulsion. Every maneuver, whether orbit adjustment, docking, or landing, depends on precise calculation of mass, thrust, and gravitational influence. Small errors can propagate over long distances, so measurements are continually compared against predictions. You observe how spacecraft computer systems integrate sensor data, calculate corrections, and guide engines with high precision. The system operates reliably because each component is informed by careful observation and mathematical modeling. You consider the coordination of these hazards and mitigations. Radiation, microgravity, vacuum, debris, temperature, isolation, and energy management interact in complex ways. Engineers and scientists integrate measurements across disciplines, modeling interactions to predict outcomes. You feel the calm logic in this approach, where every challenge is addressed through observation, calculation, and verification. The result is a controlled environment, designed to allow humans to operate safely in a realm that is inherently hostile. You rest in the awareness that human spaceflight is defined by both its fragility and its predictability. Risks are real and measurable, yet with careful observation, engineering, and planning, they can be mitigated. Each system, procedure, and schedule is designed to function in accordance with physical laws, allowing astronauts to live, move, and work in space with reliability. Your mind absorbs the understanding that safety in space is the result of deliberate, evidence-based design. As your awareness settles, you begin to sense why missions eventually paused, shaped not by technical impossibility but by the combination of financial, political, and scientific constraints, inviting reflection on the rational decisions that influence human exploration. You begin by noticing the timeline of human lunar exploration. After the initial Apollo missions, each flight provided valuable data on geology, orbital mechanics, and human performance in space. You follow the steady accumulation of knowledge, observing that by the time Apollo 17 concluded, scientists had obtained a substantial understanding of the moon's surface, composition, and environment. You sense that the scientific return from additional missions would incrementally add to knowledge, but each successive mission required the same substantial investment of time, resources, and personnel. You consider the financial constraints that influence decision-making. The cost of each mission was enormous, encompassing rocket production, spacecraft construction, astronaut training, and ground operations. You notice that, as domestic priorities shifted, the available budget for space exploration decreased relative to other government programs. Every launch demanded billions of dollars, a fact that required careful assessment of potential scientific gains versus expenditures. You follow the logic of budgetary planning, understanding that governments must weigh exploration against domestic and global needs. You reflect on the political environment of the early 1970s. The initial lunar missions were fueled by geopolitical competition, particularly with the Soviet Union. Once the United States had achieved a successful landing, the symbolic objective of demonstrating technological superiority had been largely met. You notice that the sense of urgency diminished, and political attention shifted to other priorities. Decisions regarding space exploration were therefore influenced not only by science but also by national strategy, public opinion, and shifting international relations. You observe how technological readiness played a role. While the Apollo hardware was capable of continued lunar missions, aging infrastructure, supply chains, and equipment required extensive maintenance and modernization. You trace the calculations assessing whether it was feasible to continue launches using the existing Saturn V rockets, lunar modules, and command systems. Each calculation involved risk assessment, resource allocation, and evaluation of remaining operational life. You sense that technical capability alone was insufficient to justify continued expenditure without corresponding political and financial support. You consider the rise of alternative scientific priorities. Missions to study Earth from orbit gained prominence, with satellites providing continuous observation of climate, weather patterns, and geological processes. Space stations offered a laboratory for long-duration human experiments, monitoring physiology and materials in microgravity. You notice that each of these programs required investment, offering measurable scientific returns while being more cost-effective than repeated lunar landings. The rational distribution of resources guided exploration toward activities that maximized knowledge relative to expense. You follow the emergence of robotic exploration. Automated spacecraft, rovers, and orbiters could conduct long-term observations at lower cost and risk than human missions. You trace the development of lunar orbiters that mapped the surface in high resolution, revealing geological structures, crater distributions, and potential resources. Robotic missions offered continuous data collection, unlike human missions which were limited by life support, fuel, and scheduling. You appreciate the efficiency and precision of robotic observation, noting how it complemented prior human exploration. You notice the interplay of safety, risk, and opportunity. Even with experienced crews and proven hardware, each mission carried the possibility of failure or loss. You follow calculations estimating risk probability for launch, lunar operations, and re-entry. Every estimate influenced mission approval, scheduling, and frequency. You sense the careful weighing of human safety against scientific and political objectives, understanding that prudent planning limited the number of missions to those that provided the greatest return on investment. You consider how mission priorities shifted over time. Initial flights focused on landing and surface exploration, while later objectives included longer stays, expanded geological sampling, and extended scientific instrumentation. Each new goal required additional funding, training, and equipment. You trace the gradual balancing act between what was technically achievable and what was economically sustainable. Every decision reflects a deliberate evaluation of cost-benefit ratios, demonstrating that halting lunar missions was not a matter of impossibility but of rational constraint. You observe the role of public perception. Enthusiasm for lunar exploration was initially high, with widespread media coverage and public fascination. Over time, interest waned as coverage of missions became routine and attention turned to domestic issues, social programs, and international affairs. You notice how public support influenced political willingness to fund continued missions. Decisions were therefore informed by empirical data on societal priorities, demonstrating how exploration exists within the broader context of measurable human factors. You trace the integration of all these influences: budget limitations, political shifts, technological maintenance, evolving scientific priorities, and public support combined to determine the feasible number of missions. Each factor was assessed with careful measurement and analysis, providing a rational framework for decision-making. You sense the calm logic in this convergence, understanding that exploration is guided not by passion alone but by structured evaluation of constraints and opportunities. You follow the process of mission cancellation and reallocation. Resources initially intended for additional lunar flights were redirected to programs such as Skylab, Earth observation satellites, and planetary robotic missions. You notice how engineers, scientists, and administrators collaborated to transfer knowledge, technology, and personnel efficiently. The shift in focus maximized the use of existing expertise while accommodating economic and political realities. Each adjustment was grounded in careful observation and empirical data, ensuring continuity of progress. You reflect on the enduring contributions of the Apollo missions. Even as human landings ceased, the knowledge gained, lunar geology, orbital dynamics, surface conditions, and human performance, remained foundational. You observe how subsequent missions and robotic explorers built upon this baseline, extending understanding without repeating previous work unnecessarily. You sense the continuity of scientific methodology. Measurement, observation, and analysis guide decisions, independent of external pressures. You consider how stopping human lunar missions illustrates the interplay of practical constraints with ambition. Technical capability, scientific opportunity, political interest, and economic feasibility all interact to define what is achievable. You notice that exploration is measured, deliberate, and subject to rational evaluation. The decision to halt Apollo flights reflects a careful assessment of what was necessary, feasible, and sustainable, emphasizing that cessation does not indicate failure, but rational planning. You follow the broader lesson that emerges. Exploration is an ongoing negotiation between curiosity, capability, and constraint. Every mission involves calculated trade-offs, where safety, cost, and scientific value are evaluated empirically. You sense the quiet order behind human decision-making, where rigorous measurement and rational analysis guide actions even in the context of ambitious endeavors. As your awareness settles, you begin to sense the next phase of lunar science. Robotic spacecraft, rovers, and orbiters taking over continuous observation, expanding the depth of measurement and precision without the same constraints of human presence. You begin by observing the first robotic missions to the moon, orbiters and landers designed to map, photograph, and analyze the surface. Unlike human crews, these spacecraft operate without the constraints of life support, radiation protection, or physical endurance. You notice that engineers focus on instrument reliability, redundancy, and efficiency, allowing robots to function continuously for months or even years. Every sensor, camera, and spectrometer is calibrated to provide precise measurements of surface composition, topography, and temperature. You follow the operation of lunar orbiters, which map the moon's surface in high resolution. You observe how cameras capture overlapping images, allowing scientists to construct detailed three-dimensional models. Measurements of crater diameters, mountain heights, and slope angles are recorded systematically. You sense the clarity and permanence of data collection, where every image is tagged with exact coordinates, lighting conditions, and timing. These datasets allow researchers to study geological processes without direct human intervention. You notice the deployment of robotic landers and rovers. Lander missions carry instruments to measure soil composition, detect water ice, and record temperature fluctuations. You follow how rovers navigate the terrain using onboard sensors and pre-programmed routes. Each movement is monitored from Earth, with commands adjusted based on real-time data. You feel the precision inherent in these operations, where distance, speed, and orientation are continuously calculated to ensure safe travel and accurate measurements. You consider the advantages of unmanned missions in hazardous environments. Robots are not affected by microgravity, radiation, or limited consumables. You observe how instruments can operate through extreme temperatures and over long durations without fatigue. Engineers use sensors to monitor mechanical and thermal conditions, anticipating maintenance needs and potential failures. You sense the efficiency of unmanned exploration, where data acquisition continues uninterrupted, yielding insights that would be difficult or impossible for humans to obtain. You follow the development of increasingly sophisticated instrumentation. Spectrometers analyze elemental composition of soil and rocks, while magnetometers measure local magnetic fields. Seismometers detect vibrations from impacts and internal shifts, allowing mapping of subsurface structures. You notice how these measurements provide continuous datasets, enabling long-term study of lunar geology. Each instrument is designed to function autonomously, with calibration routines and error detection to ensure reliable data. You observe how robotic missions refine understanding of water and volatiles on the moon. Instruments detect hydrogen signatures and ice deposits in permanently shadowed craters near the poles. You trace how orbiters map temperature profiles and illumination conditions, identifying regions where water ice could persist. Each detection is confirmed through multiple measurements, providing a high degree of confidence in results. You sense the precision and rigor inherent in this scientific approach. You notice the logistical advantages of robotic missions. Without the need for oxygen, food, or human life support, spacecraft can be smaller, lighter, and less costly. Launch schedules are more flexible, and longer duration observations are possible. You follow how these efficiencies allow more missions, broader coverage, and a greater diversity of scientific instruments. Every deployment maximizes data return while minimizing risk and expense. You follow the integration of orbital and surface data. High-resolution maps from orbiters are combined with rover measurements of soil mechanics, chemical composition, and local topography. You notice how scientists cross-reference datasets to identify patterns, verify models, and generate hypotheses about lunar formation, volcanic activity, and crater evolution. You sense the depth of understanding that arises from combining multiple streams of empirical data. You observe robotic missions extending beyond the moon. Spacecraft explore Mars, asteroids, and comets, providing continuous monitoring of distant environments. You notice how the design principles applied to lunar missions, autonomy, redundancy, precise measurement, are adapted to new contexts. Instruments record atmospheric composition, surface textures, gravitational fields, and mineralogy. Each mission contributes to a growing body of comparative planetary science, enhancing understanding of processes that operate across the solar system. You consider the iterative nature of robotic exploration. Data from early missions informs the design of subsequent spacecraft, improving instrumentation, navigation, and operational protocols. Engineers analyze telemetry to refine autonomy algorithms, optimize energy usage, and extend mission lifetimes. You follow how each success and failure is logged, measured, and applied to future planning. You feel the calm consistency of knowledge accumulation, where observation drives refinement in a continuous cycle. You notice the ability to operate in harsh or previously inaccessible regions. Robots reach permanently shadowed craters, steep crater walls, and rugged highlands. Measurements taken in these locations provide insight into geological history, thermal conditions, and potential resources. You follow the mapping of areas too dangerous for human exploration, understanding how robotic missions expand the boundaries of knowledge without exposing humans to unnecessary risk. You observe the precision with which robotic instruments perform repeated measurements. Temperature, magnetic field strength, radiation levels, and surface composition are recorded at regular intervals. Data is transmitted to Earth, where it is verified, calibrated, and analyzed. You notice how continuous monitoring allows detection of subtle changes over time, revealing processes such as slow thermal cycling, regolith movement, or small impact events. Each measurement adds clarity and depth to understanding. You follow the use of autonomous navigation and control. Rovers rely on sensors, cameras, and pre-programmed instructions to move across uneven terrain. Algorithms calculate wheel angles, travel speed, and obstacle avoidance, adjusting in real time. You notice how precise measurement underpins every decision, ensuring safety and maximizing data collection. The environment is unforgiving, yet careful observation and engineering allow machines to function reliably over long periods. You reflect on how robotic exploration complements human missions. Robots provide long-term observation, extensive surface coverage, and access to hazardous areas. Humans provide judgment, adaptability, and complex sampling when feasible. You sense the partnership between observation and physical presence, recognizing that continued understanding of celestial bodies depends on both autonomous measurement and selective human involvement. You notice the cumulative impact of robotic missions on lunar science. High-resolution maps, mineral composition data, temperature profiles, and radiation measurements all create a detailed understanding of the moon's environment. Each dataset is cross-checked, verified, and used to plan future exploration. You feel the calm authority of evidence-based knowledge, where precision, repetition, and measurement ensure that conclusions are reliable. As your awareness rests on these observations, you begin to sense the gradual refinement of lunar knowledge, where contemporary missions continue to expand understanding of geology, water, and resources. Measurement and data-driven exploration quietly guide future decisions, providing a foundation for returning humans safely and effectively. You begin by observing the contemporary efforts to study the moon, where orbiters and landers carry advanced instruments designed to gather precise measurements. Modern spacecraft, equipped with high-resolution cameras, spectrometers, and laser altimeters, provide data with accuracy unimaginable during the early Apollo era. You follow how scientists analyze surface composition, volcanic deposits, and crater morphology, gradually refining maps and models with each orbit. Every measurement contributes to a more complete understanding of lunar geology and processes. You notice the focus on polar regions, where permanently shadowed craters may contain water ice. Instruments on orbiters detect hydrogen signatures and map thermal conditions, revealing areas where ice can remain stable over geological timescales. You follow how landers and impact probes measure the quantity and distribution of volatiles, confirming orbital observations. Each dataset is carefully verified and cross-referenced, building confidence in conclusions about the Moon's potential resources. You observe the systematic study of lunar regolith, the layer of fragmented rock covering the surface. Recent analyses involve remote sensing, sample return missions, and in situ measurements. You trace how scientists determine particle size, composition, and distribution, as well as the effects of micrometeoroid impacts. Each measurement contributes to understanding the processes that shaped the lunar surface over billions of years. You sense the careful layering of knowledge, where new observations refine prior models rather than replacing them. You follow the study of lunar volcanic history. Orbital imaging and spectral data identify ancient lava flows, volcanic domes, and pyroclastic deposits. You notice how scientists measure chemical composition to infer the temperature, viscosity, and eruption mechanisms of lunar volcanism. Crater counting techniques provide relative dating, allowing researchers to establish timelines for volcanic activity. You feel the steady accumulation of evidence, revealing the Moon as a record of its own geological past. You consider the importance of impact cratering in shaping the lunar surface. High-resolution images and topographical maps allow scientists to measure crater size, depth, and distribution. You trace how these data are used to estimate the frequency and energy of past impacts, as well as the processes that modify craters over time. Each measurement informs models of planetary evolution and provides context for understanding the history of the inner solar system. You notice how lunar missions contribute to understanding Earth-Moon interactions. Tidal forces, orbital mechanics, and rotational dynamics are studied using precise laser ranging to retroreflectors left on the lunar surface. You follow how scientists measure the distance between Earth and the Moon with centimeter-scale accuracy. These measurements reveal subtle changes in the Moon's orbit and rotation, providing insight into the long-term evolution of both bodies. You sense the precision and consistency of data collection over decades. You observe the analysis of return samples. Modern techniques, including mass spectrometry and electron microscopy, allow scientists to determine isotopic ratios, mineral phases, and trace elements with high precision. Each analysis provides insight into the Moon's formation, differentiation, and thermal history. You notice how these studies refine prior interpretations of lunar origin, confirming and expanding the understanding gained during earlier missions. Every measurement is repeated and verified, ensuring confidence in conclusions. You follow the ongoing search for potential resources. Mapping of water ice, helium-3, and rare minerals informs planning for future exploration and utilization. Orbital instruments detect elemental abundances, while landers test extraction techniques in controlled experiments. Each dataset allows for a realistic assessment of feasibility, guiding decisions based on quantifiable evidence rather than speculation. You feel the calm assurance that arises from precise measurement and careful evaluation of options. You notice how contemporary missions also focus on environmental monitoring. Radiation levels, micrometeoroid flux, and thermal variations are measured continuously to understand hazards for future human explorers. Instruments collect data on the solar wind, magnetic anomalies, and surface charging, providing information critical for both engineering design and astronaut safety. You sense the subtle complexity of the lunar environment and the systematic approach scientists use to quantify it. You consider the importance of international collaboration. Multiple space agencies operate orbiters, landers, and research programs, sharing data openly or in coordinated studies. You follow how scientists compare measurements from different instruments, validate findings, and refine models. Each collaborative effort strengthens conclusions, providing a more robust understanding of lunar conditions. You feel the quiet efficiency of shared observation, where multiple perspectives enhance reliability and depth of knowledge. You observe the integration of robotic, orbital, and sample-based data. Topography, chemical composition, thermal properties, and physical measurements are combined to produce comprehensive maps and models. You trace how scientists use this integrated approach to study the evolution of lunar basins, volcanic plains, and highland regions. Every cross-validated measurement adds precision, allowing the scientific community to reconstruct geological processes and environmental conditions with increasing confidence. You follow the study of regolith mechanics for landing and construction planning. Data on particle cohesion, bulk density, and thermal behavior informs both rover mobility and habitat design. Engineers analyze measurements to predict traction, excavation feasibility, and the stability of structures. You notice the careful calibration of instruments to measure these properties accurately, emphasizing the role of empirical evidence in practical planning for human and robotic operations. You consider how ongoing lunar research informs broader planetary science. By comparing lunar features with terrestrial analogs, scientists develop models for crater formation, volcanic processes, and surface evolution elsewhere. You notice how measurements of mineralogy, thermal gradients, and regolith properties are applied to other celestial bodies, including Mars, asteroids, and moons of the outer planets. Each observation contributes to a cumulative understanding of planetary systems. You observe how incremental data collection guides mission planning. Thermal maps indicate optimal landing sites, spectral data informs resource extraction strategies, and topographic models support navigation and hazard avoidance. Each measurement is repeated and validated, providing a foundation for decisions grounded in observation rather than assumption. You sense the quiet accumulation of knowledge, layer by layer, forming a coherent understanding of the lunar environment. You reflect on the moon's continuing influence on Earth. Its gravitational pull affects tides, rotation, and long-term orbital stability. By studying the moon's history, scientists also gain insight into Earth's early geological evolution, including impact frequency, crust formation, and thermal history. Each measurement, whether on the surface, in orbit, or from returned samples, informs a broader understanding of the Earth-Moon system. You feel the calm interconnectedness of measurement, observation, and scientific inference. You notice the systematic approach to data verification. Each instrument undergoes calibration, error checking, and cross-validation. Measurements are compared against models and prior observations, ensuring accuracy. You follow how unexpected results are investigated, hypotheses tested, and findings either confirmed or revised. The process exemplifies scientific rigor, where conclusions are derived from repeated, verifiable observation rather than assumption. You rest in the awareness that contemporary lunar science is a product of continuous measurement, careful verification, and the integration of multiple sources of data. Knowledge advances gradually, supported by technology, empirical evidence, and meticulous planning. You feel the calm authority of science, where each observation contributes to a growing, reliable understanding of another world. As your awareness settles, you begin to sense the future trajectory of exploration, where human presence may return, guided by accumulated knowledge, precise measurement, and careful planning of rockets, habitats, and life support systems. You begin by observing the current plans for returning humans to the moon, where decades of data, robotic exploration, and technological development inform every step. Modern programs like NASA's Artemis aim to build upon the foundation established during Apollo, applying improved engineering, robotics, and life support systems. You notice the careful sequencing of launches, orbital insertions, and landings, all designed to ensure safety, efficiency, and maximum scientific return. Every calculation is grounded in physics, tested extensively through simulation and previous missions. You follow the development of new rockets, designed to carry larger payloads and cruise with enhanced reliability. Engines are tested under extreme conditions to measure thrust, combustion stability, and fuel efficiency. You observe the application of trajectory planning, where orbital mechanics dictate launch windows, transfer paths, and lunar insertion angles. Each parameter is calculated precisely to minimize fuel consumption, ensure accurate landing, and maintain predictable spacecraft motion. You sense the careful balance between energy, mass, and gravitational influence, which governs every maneuver. You notice the design of spacecraft for human occupancy, where life support systems regulate oxygen, carbon dioxide, temperature, and humidity. Redundant systems monitor pressure, air composition, and water availability, allowing continuous operation even if one component fails. You follow the analysis of thermal loads, shielding, and insulation, which protect occupants from both solar radiation and the extremes of lunar day and night. Every system is validated through testing and modeling, ensuring predictability and reliability in an inherently hostile environment. You trace the engineering of lunar habitats. Modules are designed to provide stable living and working conditions on the surface, including shielding from micrometeoroids and radiation. Structural integrity, thermal control, and air circulation are verified through computational modeling and material testing. You notice how engineers simulate crew activity, equipment placement, and environmental control to optimize space usage while maintaining safety. Each measurement ensures that habitats function as intended, supporting sustained human presence. You follow the planning of mission logistics, including cargo transport, power supply, and surface mobility. Rovers, cranes, and robotic assistants are integrated to support both scientific and operational objectives. You observe how orbital calculations guide delivery of supplies, placement of habitats, and alignment of solar arrays. Energy generation, storage, and distribution are modeled in detail to ensure sufficient power for both life support and scientific instruments. Every calculation is verified with empirical data and simulation results. You consider the integration of scientific goals into mission planning. Lunar missions aim to investigate geology, search for water ice, and test technologies for future exploration. Instruments are selected and positioned to maximize data collection within mass, volume, and energy constraints. You notice how precise orbital placement of satellites and landers enhances coverage and allows cross-validation with in-situ measurements. Each decision is grounded in a measured balance of scientific return, operational feasibility, and crew safety. You observe the attention given to astronaut training. Crews practice in analog environments on Earth, learning navigation, scientific sampling, equipment operation, and emergency procedures. Simulations include microgravity training, extravehicular activity, and habitat operations. You follow how these exercises are informed by previous missions and current scientific understanding, ensuring that astronauts can operate effectively under lunar conditions. Every skill is measured, monitored, and refined to achieve predictable outcomes. You notice the application of robotics to supplement human activity. Robotic assistants prepare sites, transport materials, and perform measurements in areas that may be hazardous or distant from human habitats. You follow how autonomous or teleoperated systems reduce risk, increase efficiency, and extend operational range. Each task is planned and tested to ensure reliability, with performance evaluated using precise instrumentation and observation. You feel the quiet precision of collaboration between human and machine. You consider the scheduling and coordination of launches. Orbital mechanics dictate optimal launch windows, where fuel usage is minimized and trajectories align with lunar orbits. You observe calculations for interplanetary travel, translunar injection, and lunar orbit insertion, each relying on accurate measurements of gravitational forces, spacecraft mass, and velocity. You notice how timing adjustments account for Earth's rotation, lunar position, and solar influence. Every maneuver is verified and rehearsed to reduce uncertainty and maximize predictability. You follow the analysis of risk management. Engineers and planners evaluate every potential hazard, from system failure to environmental extremes. Contingency procedures are developed and tested repeatedly. You notice how redundancy is incorporated across systems, including life support, communications, power, and mobility. Each scenario is simulated, measured, and used to refine mission planning. You sense the calm logic of preparation, where empirical evidence underpins every decision. You observe the use of modern materials and construction techniques. Lightweight alloys, radiation-resistant composites, and advanced thermal coatings are employed to ensure durability and efficiency. You follow laboratory testing of these materials under conditions simulating lunar temperature swings, vacuum, and micrometeoroid impacts. Measurements of strength, thermal conductivity, and wear inform final design choices. Every detail reflects the application of precise physical understanding to achieve reliable performance. You notice the role of international collaboration. Multiple countries contribute hardware, expertise, and scientific objectives. You follow how data from orbital satellites, landers, and rovers are shared, integrated, and analyzed collectively. Every dataset is verified, cross-referenced, and incorporated into mission planning. You sense the efficiency of this cooperative approach, where the reliability and depth of knowledge are enhanced by multiple independent measurements. You consider the testing of new technologies. In situ resource utilization experiments, advanced life support modules, and new propulsion systems are evaluated on robotic platforms before being used by humans. You observe measurements of oxygen extraction, water filtration, and surface excavation, ensuring that operations are predictable and safe. Each test informs subsequent engineering decisions, reducing risk and increasing operational confidence. You follow the careful balance of mission duration and crew safety. Time spent on the lunar surface is limited by consumables, radiation exposure, and physiological stress. Calculations ensure sufficient reserves while allowing meaningful scientific work. You notice how orbital dynamics, energy usage, and environmental measurements all inform planning. Every schedule is optimized through precise modeling and repeated validation. You reflect on the deliberate and cumulative nature of planning. Every decision, calculation, and test is grounded in evidence and past experience. Risk is mitigated, resources are allocated efficiently, and objectives are prioritized based on measurable outcomes. You sense the calm precision of human ingenuity, where each component of the mission is integrated to produce a coherent, predictable, and safe operation. You rest in the understanding that returning to the moon is not a spontaneous endeavor but a carefully orchestrated scientific undertaking. Every rocket, module, instrument, and procedure has been measured, tested, and refined to ensure that humans can explore once more with confidence, clarity, and safety. The moon awaits as both a laboratory and a teacher, its environment precisely mapped, measured, and prepared for renewed study. You begin by observing the moon as a source of continuous learning. Its surface records billions of years of cosmic history, preserving impacts, volcanic activity, and tectonic shifts. You notice that every crater, ridge, and plain offers measurable information about forces that have shaped both the moon and the broader solar system. Through careful observation and precise measurement, scientists have been able to reconstruct its geological history, revealing processes that are otherwise invisible on Earth, where erosion and plate tectonics erase traces over time. You follow the study of orbital mechanics. The moon's motion around Earth illustrates the fundamental principles of gravity and momentum. Scientists measure its orbit with extraordinary precision, observing variations caused by tidal forces, gravitational interactions with other celestial bodies, and subtle effects predicted by general relativity. You notice how long-term laser ranging to retroreflectors left by astronauts provides exact distances, allowing calculations that refine models of both lunar and Earth motion. Each measurement reinforces understanding of celestial mechanics. You observe the contribution of lunar exploration to geology. Sample return missions provide direct evidence of rock composition, mineral distribution, and age. Analyses using spectroscopy, radiometric dating, and microscopy reveal the moon's formation, differentiation, and volcanic history. You follow how scientists integrate these findings with orbital observations to produce comprehensive geological maps, identifying regions with distinct characteristics. Every data point adds depth to knowledge, creating a layered understanding of planetary evolution. You consider the moon's role in understanding planetary science more broadly. Its relative stability, lack of atmosphere, and preserved surface make it an ideal laboratory for studying impact cratering, regolith formation, and volcanic processes. By comparing lunar measurements with terrestrial analogs, scientists gain insight into similar processes on Mars, Mercury, and other rocky bodies. You sense the calm logic of using empirical observation to extrapolate understanding across the solar system. You notice the lessons about human physiology and engineering. Apollo missions provided critical data on the effects of microgravity, radiation exposure, and extended isolation. Life support systems, habitat design, and extravehicular activity procedures were tested and refined through direct experience. You follow how this knowledge informs both space station operations and future planning for longer planetary missions. Each measured response, each logged physiological parameter, adds to a body of knowledge that ensures safety and effectiveness. You follow the accumulation of long-term observational data. Lunar orbiters continuously measure topography, gravitational anomalies, and surface temperatures. Instruments track subtle shifts in regolith, radiation exposure, and magnetic field variations. You notice how repeated, precise measurements allow scientists to detect trends over time, revealing slow geological and environmental changes. This consistent monitoring demonstrates how patient, methodical observation gradually produces comprehensive understanding. You observe the moon's contribution to understanding Earth. Tidal interactions, which influence ocean levels, rotational speed, and climate patterns, are measured and modeled using lunar data. These measurements refine understanding of Earth's rotational dynamics, long-term stability, and energy transfer within the Earth-Moon system. You sense the quiet interconnection of celestial bodies, where precise observation of one informs knowledge of another. You notice the role of technology in enabling discovery. From early telescopic studies to modern orbiters, robotic landers, and sample analyses, each advance has improved accuracy and expanded capabilities. Instruments measure electromagnetic spectra, mineralogy, temperature gradients, and gravitational fields with increasing precision. You follow how repeated refinement of tools enhances confidence in findings, producing a steady accumulation of validated knowledge. You consider the cumulative nature of lunar exploration. Human and robotic missions, orbital observations, and laboratory analyses are integrated into coherent models of lunar history and structure. You notice that no single mission provides complete understanding. Rather, knowledge grows incrementally, each measurement building on prior work. This layered approach exemplifies scientific methodology: observation, measurement, verification, and refinement. Each cycle adds clarity, reduces uncertainty, and informs future planning. You follow the lessons in resource utilization and preparation. Studies of water ice, regolith mechanics, and surface composition inform strategies for in-situ resource use. Experiments with oxygen extraction, excavation, and habitat construction are carefully measured and analyzed. You notice how evidence-based planning ensures that future exploration can be sustainable, safe, and scientifically productive. The moon becomes a laboratory for both fundamental science and applied engineering. You observe how lunar data informs modeling and prediction. Measurements of surface temperatures, radiation exposure, and orbital dynamics allow simulations that guide both robotic and human operations. Each simulation is validated against empirical data, providing confidence in operational planning. You sense the quiet power of integrating observation with computation to extend understanding beyond direct measurement. You consider the philosophical implications of this work. The moon illustrates the limits of human presence, the need for careful preparation, and the rewards of patient observation. You notice that exploration is not a matter of impulsive action but a disciplined pursuit of knowledge. Every measurement, calculation, and observation is a deliberate step toward understanding, guided by principles of accuracy, repeatability, and empirical evidence. You follow the systematic study of lunar phenomena such as dust dynamics, micrometeoroid impacts, and thermal cycling. Instruments measure dust levitation, impact frequency, and surface temperature fluctuations. Each dataset is analyzed in relation to prior observations, building models that predict behavior in different regions and conditions. You sense the precision and reliability of the knowledge, where patterns emerge only after repeated measurement and careful evaluation. You observe the educational role of the moon. Data and images inform research, training, and planning for both scientists and engineers. By studying precise measurements, humans learn to navigate, operate, and survive in extraterrestrial environments. Every calibrated instrument, every analyzed sample, contributes to a growing understanding that supports future exploration. You notice the calm continuity of scientific learning, where lessons accumulate steadily over decades. You reflect on the moon's enduring influence. It has guided scientific inquiry, informed technological development, and provided a laboratory for understanding both celestial and terrestrial processes. Measurements of geology, gravity, orbital motion, and radiation form a precise record of observation and analysis. You notice how each generation of study builds upon the last, gradually deepening understanding while ensuring reliability. You rest in the awareness that the moon continues to teach, not through stories or myth, but through measurement, observation, and careful experimentation. Its quiet presence allows the patient accumulation of knowledge, inviting precise study and reflection. You sense the calm continuity of science, the way evidence steadily guides understanding, and the way observation transforms curiosity into measured insight. Each piece of data, every calculation, and every verified observation forms a chain of knowledge, gently expanding awareness while leaving the mind serene and attentive. As your attention drifts, you begin to sense the broader cosmos, where the principles learned from the moon guide exploration of planets, asteroids, and distant stars, offering new frontiers of measured discovery.